So we're still looking at first order rate law. And first order rate law follows the equation that I gave you there on that equation sheet. But this says that we need to confirm or verify that this rate law is first order and then calculate the value of the rate constant. So in order for us to confirm that it's a first order rate law, we could use the differential rate law, but that has the comparison of two different reactants based on their concentration and time. Based on just their concentrations and the rates. This now, integrated rate law has a different variable, and that's time. Right? We can't just use the regular rate law that we know because we don't have the initial rates. Right? In the initial rate method for differential rate law, we can compare initial rates versus concentration and how those are affected. This time we're looking at how time affects our concentrations. So, in order for us to verify that this rate law is first order, we have to graph it. Okay, there's not going to be very many questions that I ask you to graph it, but I want to show you this one because it does everything, right? We have to graph it, and then we'll do some solving. There's one problem on your homework that asks you to do that as well, and then the rest just solve from based on what you know about first order. So, let's go ahead and do that. If I have to verify that the rate law is first order, calculate the value of the rate constant. So, when I calculate and when I look at first order rate laws, if I were to graph them, my graph would look something like this. My graph would be the natural log of my concentration of my reactant, N2O5, over time, right? If it's a first order reaction, I would graph the natural log of my reactant over time, okay? And so that means in order to get that graph data, I need to make another portion or whatever, another spot in my data table in which I have the data of the natural log of all of my concentrations. Okay? Do you remember the equation for the first order integrated rate law?
Or natural log concentration.
Yep. At a certain time
is equal to...
Right, good. So here's our equation for the integrated rate law for first order reactions. It lines up just like Y equals mx plus b, right? Y equals mx plus b. So that's the reason we're able to graph this and see this data. Okay, and so when I've said it's going to be the natural log of the concentration over time, that's because the y-axis, the y variable lines up with natural log, the x-axis lines up with time. Okay? So, when I'm going to go, I have to go through now and find the natural log of all of those concentrations. So go ahead and grab your calculator out and get that data for me so we can fill in our table. So natural log of 0.1 is negative 2.30. Anybody have the next one for me?
Negative 2.65.
Okay. Just give me the next ones when you have them.
Negative 2.99.
2.99. Okay, next one. I got negative 3.69. Is that what we had on that one?
Yeah.
Natural log 0.0125.
Negative 4.38.
Thank you. And then last one. 0.062.
Negative 5.08.
Thank you. Okay, so we've got now the data in order to construct our graph. Okay, all we're looking for in this graph is that if we can confirm that this natural log versus time graph results in a straight line, then that's confirming for us that it's a first order reaction. Okay, that's what it does. It just confirms to us that it's first order. If my natural log versus time plots can give us a straight line, we'll see that we can confirm that it's first order. So I'm going to go ahead and graph that. My scale might not be perfect here, but we'll go ahead and graph it as best we can. Okay, it is negative, so I'm going to go ahead and make my graph where this is time. This is natural log of N2O5. Okay, my initial time is 0, and I'm starting at let me go one more. And then my time is moving at increments of, I don't know, we'll just call it 50 seconds, I guess. Kind of messy here. I'm not having enough room, but that's okay. Okay. So your graph doesn't have to be perfectly to scale, but we're going to do as best we can. So my first point is going to be 0 and negative 2.30. So somewhere in that range. Okay, can you see that on there? Next one is at 50 seconds, and we're at negative 2.65. So here's 50 seconds. I'm going to scale down to 2.65, so somewhere in there. The next one at 100 seconds is basically negative 3. At 200 seconds, we get to negative 3.69. At 300 seconds, we get to negative 4.38. And at 400 seconds, we get to negative 5.08. Okay, so we want to confirm that this is a straight line. Okay, we did our best to draw it to scale here, and if we had made our efforts a little bit better, our line might have been a little bit more straight. But do those lines generally fall on that straight line? Do our plot points generally fall on that line of best fit? Yeah. So that's just our confirmation that we have a first order reaction. If you're not sure what order of reaction it is, you graph it a few different ways, and we'll talk through that as we go into second order and zero order. But if we have a graph, if you have a problem that says a graph of natural log versus time results in a straight line, that tells you that it's first order, right? If it says a graph of natural log versus time results in a straight line, that's going to be a first order reaction. Because second order reactions don't graph with natural log. They graph with 1 over a concentration. And zero order reactions don't graph with natural log. They graph with just the concentration itself. Okay, so natural log and first order go together. Okay, so we've confirmed now that our rate is a first order reaction, and we need to calculate the value of the rate constant, which is K. So I can come up here and look at my relationship and say, I can solve for K just by finding the slope of my line. Right? Just by finding the slope of my line, I'm able to identify the rate constant. Okay? Now here's the important part, and your book kind of points this out, and the video pointed it out as well, but this line of best fit, for sure, has to go through the first and the last point. Right? It has to. The other points might not fall exactly on that line. So when you calculate slope, you need to find the slope based on the data from the last point and the first point. Okay? How do you calculate slope of a straight line?
Rise over run.
Yeah, rise over run. Change in y over change in x. So that's all we're going to do here. So if I'm going to calculate the slope, I'm going to take the change in y, which is negative 5.08, minus the initial, so negative 2.30, over my change in time, which would be 400 minus 0, so just 400. And so then I'm going to run that math knowing that a minus a negative turns that into a positive. Negative 5.08 plus 2.30 gives me negative 2.78 divided by 400 gives me a value of negative 0.00695. Okay, that's my slope. So if we go up and look at our reaction, we know that M is equal to negative K. So what does that mean the actual value of my rate constant is? It's positive. So I would say that my K value is 0.00695. And then the units for that, natural log here would be moles over liter. Actually, no, it's not. Natural log doesn't have that unit. it's just seconds here, so our unit is just per second, or 1 over seconds. Okay, kind of got lost there. So the natural log of that concentration doesn't have the concentration units, right? It's just 1 over seconds. Okay, you might be asked after this to take this K value and solve what's the concentration after 500 seconds? And you would plug it back into your integrated rate law, knowing that, okay, I know my K, I know my T, I know my initial concentration. I could solve for my final concentration there. Does that make sense?
The initial concentration is...
If I was going to do that, let's just go ahead and let's just do that for fun, okay? So let's find out what's the concentration after 500 seconds. I'm going to go plug it into my equation. Let me give myself some room here. If I want to know the concentration after 500 seconds, I'm going to take natural log of my concentration at 500 seconds. You don't have to write the time there if you don't want to. Remember, this is just like a label for us. That's not, you're not multiplying it by 500 or anything like that. We're just saying the concentration at 500 seconds equals negative 0.00695 times 500 seconds plus the natural log of my initial concentration, which was 0.10. Okay, so if I run the math on that, I know my natural log already is negative 2.30. 0.00695 times 500 gives me negative 3.4.
Would K be negative?
Yep, I added the negative right there because negative's in the equation.
So negative M equals K.
Right, and then when you plug it back in, right, it comes back to being negative. Right. Okay, so I'm going to set up my whole left side of the equation equals natural log of my concentration. So now if I take negative 3.475 minus 2.30, that gives me negative 5.775 equals natural log of A. So do you know how to get rid of the natural log?
Take it to the E.
You take it to the E. So instead, if this was just any other coefficient, we would divide by ln, but that's not really what natural log does. So in your calculator, you're going to use second natural log to get rid of the natural log. Okay, so in my calculator, I'm going to go second natural log, which gives me a small e to a caret, and then in that exponent, you're going to put that whole number, so negative 5.775, and then that gives me my concentration of A, or of N2O5, whatever I was looking for, which is 0.003. I did plug the negative into that exponent. It gave me E caret, and so then negative 5.775. And so that's my concentration after 500 seconds.
Oh, wait, I got...
You've done that, look at your data table and see, does that seem rational, right? Was it rational that my concentration was cut in half from 400 to 500 seconds? Yeah, right? That follows the pattern on the other ones. If we look here at the half-life, which we haven't got into just quite yet, but if we look here at the half-life, from 100 to 200 seconds, my concentration was cut in half. Then after another 100 seconds, my concentration was cut in half. After another 100 seconds, my concentration was cut in half. So the half-life for this reaction has to be 100 seconds. Right? My concentration was cut in half.
So, couldn't...
Okay, this one says a first order reaction is 35% complete. At the end of 55 minutes, what's the value of K? What's the value of our rate constant? So this one is a little bit different. We don't know anything about its initial concentrations. All we know is that it's 35% completed after that time. So you need to focus on just the proportion, really, right? We can make up any initial concentration we want, knowing that if it's 35% done, how much of it is left? 65%, right, 65%. So here's how I would set up the problem if I was doing it. I know that my first order reaction is going to have the equation natural log of A equals negative KT plus natural log of A initial. Okay? And so I don't know what my initial concentration is, but but I can pick a really easy number for me to be able to compare this, okay? So I'm going to say that my initial concentration is just 1. All right, my time I know is 55 minutes. I'm solving for K, so that's got to stay. If my initial concentration is 1 and it's 35% complete after that point, what's my final concentration going to be?
65.
Okay, yeah, not 65, but 0.65.
Yeah.
Right? If my initial concentration was 1, it's 0.65. If my initial concentration you picked to be 10, then it would be 6.5. If you picked it to be 100, it would be 65, right? It's just about the proportion.
Wait, can time stay in minutes?
Yeah, time can stay in minutes. That means when we get our units for our rate constant, it's just going to be like 1 over minutes instead of 1 over seconds like usual. Okay? So let's go ahead and run that math. Natural log of 0.65 negative 0.431 equals negative 55K plus... Oh, natural log of 1 is just 0, right? So that falls off the end. So that means we're going to take negative 4.31 divided by negative 55. And I get a K value of 0.0078. And the units here are just going to be 1 over minutes, right? Because the time that we put into our equation was in minutes. Right? Because if we're talking about concentration here, this is going to be moles per liter. This is going to be moles per liter. So it's going to end up canceling out on both sides. So all you're left with is your time unit there.